Okay, before I had to stop, but now we can continue with applying simple procedures. Section 3.2.2. When we introduced the substitution model in section 1.1.5, we showed how the combination F5 evaluates to 136 given the following procedure definitions. And we can analyze the same example using the environment model. Figure 3.4 shows the three procedure objects created by evaluating the definitions of f square and sum of squares in the global environment. Each procedure object consists of some code together with a pointer to the global environment. In figure 3.5, we see the environment structure created by evaluating the expression f5. The call to f creates a new environment E1 beginning with a frame in which a, the formal parameter of f, is bound to the argument 5. In E1 we evaluate the body of f. To evaluate this combination, we first evaluate the subexpressions. The first subexpression, sum of squares, has a value that is a procedure object. Notice how this value is found. We first look in the first frame of E1, which contains no binding for sum of squares. Then we proceed to the enclosing environment, that is the global environment, and find the binding shown in figure 3.4. The other two subexpressions are evaluated by applying the primitive operations plus and star to evaluate the two combination plus A1 and star A2 to obtain 6 and 10 respectively. Procedure objects in the global frame. Okay, so sum of squares, square, and f are all defined in global environment. Now we apply the procedure object sum of squares to the arguments 6 and 10. This results in a new environment E2 in which the formal parameters x and y are bound to the arguments. Within E2 we evaluate the combination plus square x square y, and this leads us to evaluate square x where square is found in the global frame and x is 6. Once again we set up a new environment E3 in which x is bound to 6, and within these we evaluate the body of square, which is star xx. Also, as part of applying sum of squares, we must evaluate the subexpressions, square y, where y is 10. This second call to square creates another environment, E4, in which x, the formal parameter of square, is bound to 10. And within E4 we must evaluate star xx. Okay. Environments created by evaluating F5 using the procedures in figure 3.4. So we create 4 environments: E1, E2, E3, E4. The important point to observe is that each call to square creates a new environment containing a binding for x. We can see here how the different frames serve to keep separate the different local variables all named x. Notice that each frame created by square points to the global environment, since this is the environment indicated by the square procedure object. Yes, because the procedure object contains the code and a pointer to the environment, and in this case is the global environment. After the sub-expressions are evaluated, the results are returned. The values generated by the two calls to square are added by sum of squares, and this result is returned by f. Since our focus here is on the environment structures, we will not dwell on how these returned values are passed from call to call. However, this is also an important aspect of the evaluation process, and we will return to it in detail in chapter 5. Then we have a bunch of exercises, but we can skip to section 3.2.3, frames as the repository of local state. We can turn to the environment model to see how procedures and assignment can be used to represent objects with local state. As an example, consider the withdrawal processor from section 3.1.1 created by calling the procedure. Okay. Let us describe the evaluation of define, W1, make withdraw, for okay. Figure 3.6 shows the result of defining the make withdraw procedure in the global environment. This produces a procedure object that contains a pointer to the global environment. So far, this is no different from the examples we have already seen, except that the body of the procedure is itself a lambda expression. The interesting part of the computation happens when we apply the procedure make withdraw to an argument. Okay. So this is the result of evaluating define W1, make withdraw 100. We begin as usual by setting up an environment E1 in which the formal parameter balance is bound to the argument 100. Within this environment, we evaluate the body of make withdraw, namely the lambda expression. This constructs a new procedure object whose code is specified by the lambda and whose environment is E1, the environment in which the lambda was evaluated to produce the procedure. The resulting procedure object is the value returned by the call to make withdraw. This is bound to W1 in the global environment, since the define itself is being evaluated in the global environment. Figure 3.7 shows the resulting environment structure. Okay. Still all very abstract to me, and I feel like I didn't yet understood what this environment and frames are when we practically code, but I will understand. Okay, we begin by constructing a frame in which amount, the formal parameter of W1, is bound to the argument 50. The crucial point to observe is that this frame has as its enclosing environment not the global environment, but rather the environment E1, because this is the environment that is specified by the W1 procedure object. Within this new environment, we evaluate the body of the procedure. Okay. The resulting environment structure is shown in figure 3.8. The expression being evaluated references both amount and balance. Amount will be found in the first frame in the environment, while balance will be found by following the enclosing environment pointer to E1. Okay. When the set is executed, the binding of balance in E1 is changed. At the completion of the call to W1, balance is 50, and the frame that contains balance is still pointed to by the procedure object W1. The frame that binds a mount in which we executed the code that changed balance is no longer relevant since the procedure call that constructed it has terminated, and there are no pointers to that frame from other parts of the environment. Next time W1 is called, this will build a new frame that binds a mount and whose enclosing environment is E1. We see that E1 serves as the place that holds the local state variable for the procedure object W1. Figure 3.9 shows the situation after the call to W1. Observe what happens when we create a second withdraw object by making another call to make withdraw. Okay, I guess we have two different environments now. This produces the environment structure of figure 3.10, which shows that W2 is a procedure object that is a pair with some code and environment. The environment E2 for W2 was created by the call to make withdraw. It contains a frame with its own local binding for balance. On the other hand, W1 and W2 have the same code, the code specified by the lambda expression in the body of make withdraw. Whether W1 and W2 share the same physical code stored in the computer or whether they each keep a copy of the code is a detail of implementation. For the interpreter we implement in chapter 4, the code is in fact shared. Okay, so it is in the same memory address. We see here why W1 and W2 behave as independent objects. Calls to W1 reference the state variable balance stored in E1, whereas calls to W2 reference the balance stored in E2. Thus, changes to the local state of one object do not affect the other object. Okay, clear. Exercise. Section 3.2.4 Internal definitions. Section 1.1.8 introduced the idea that procedures can have internal definitions, thus leading to a block structure as in the following procedure to compute square roots. Okay, I remember that. Now we can use the environment model to see why these internal definitions behave as desired. Figure 3.11 shows the point in the evaluation of the expression where the internal procedure good enough has been called for the first time with guess equal to 1. Observe the structure of the environment. SQRT is a symbol in the global environment that is bound to a procedure object whose associated environment is the global environment. When SQRT was called, a new environment E1 was formed, subordinate to the global environment in which the parameter x is bound to 2. The body of SQRT was then evaluated in E1. Since the first expression in the body of SQRT is good enough, evaluating this expression defined the procedure good enough in the environment E1. To be more precise, the symbol good enough was added to the first frame of E1, bound to a procedure object associated environment is E1. Similarly, improve and SQRT iter were defined as procedures in E1. For conciseness, figure 3.11 shows only the procedure object for good enough. Okay. Okay. After the local procedures were defined, the expression SQRT iter 1.0 was evaluated, still in environment E1. So the procedure object bound to SQRT iter in E1 was called with 1 as an argument. This created an environment E2 in which guess, the parameter of SQRT iter, is bound to 1. SQRT iter in turn called good enough with the value of guess from E2 as the argument for good enough. This set up another environment, E3, in which guess, the parameter of good enough, is bound to 1. Although SQRT iter and good enough both have a parameter named guess, these are two distinct local variables located in different frames. Also, E2 and E3 both have E1 as their enclosing environment. Because the SQRT iter and good enough procedures both have E1 as their environment part. One consequence of this is that the symbol X that appears in the body of good enough will reference the binding of X that appears in E1, namely the value of X with which the original SQRT procedure was called. The environment model thus explains the two key properties that make local procedure definitions a useful technique for modularizing programs. The names of the local procedures do not interfere with names external to the enclosing procedure, because the local procedure names will be bound in the frame that the procedure creates when it is run, rather than being bound in the global environment. The local procedures can access the arguments of the enclosing procedure simply by using parameter names as free variables. The local procedures can access the arguments of the enclosing procedure simply by using parameter names as free variables. This is because the body of the local procedure is evaluated in an environment that is subordinate to the evaluation environment for the enclosing procedure. Local procedures can access the arguments of the enclosing procedure simply by using parameters name. The body of the local procedure is evaluated in an environment that is subordinate to the evaluation environment for the enclosing procedure. Okay, I guess. I understood. Okay. And I stop here. And the next time we will continue with section 3.3, modeling with mutable data. Okay, see you in the next one. Ciao, ciao.